So I have an airfoil. I have an airfoil right here. And in this case with 0-degree flap deflection. So I have a center of pressure. And I have, of course, some lift generated and some drag generated. Okay, so what happens if I basically increase the flap deflection? So flap deflection usually we summarize by the flap deflection angle, right? So we say that the clean configuration means that the flap deflection is 0. The flap deflection is 0 degrees. That is called a clean configuration. And if the flap deflection is not equal to 0, in that case, that is a configured airfoil. Okay, so what happens when I deflect the flaps? I generate a so-called flap deflection. The center of pressure is also going to move, but we're not going to consider the effect of that for now. But what we're going to examine is that there's going to be a delta L, so an increase in the lift, basically, because of this increase in the flap deflection. And as you know, there's also going to be an increase in the drag because of the flap deflection, right? So if I wanted to draw down the CL alpha curve of the airfoil, so this would be the lift coefficient, this will be the angle of attack, and this is the CL alpha curve of a clean configuration aircraft. So when the flap deflection is basically 0. Right, so this is what it looks like. And if I deflect the flaps, it's basically going to shift to the left and up, like this. And only in case when we talk about trailing edge flaps, right? So we're only talking about the trailing edge flaps right now. Trailing edge flaps. And we're examining the effect of that. Right, so this is the configured flaps. So the delta flap, let's say, is 10 degrees, for example. But we can see that for a given angle of attack, so for a given angle of attack, this one, there's going to be an increase in the lift coefficient, right? This was the lift coefficient initially with the flap 0, and this is the lift coefficient with the flaps 10, right? So we can see that there's this delta CL, right? So this increase in the lift coefficient, so there's this increase in the lift coefficient. If there's an increase in the lift coefficient, if we write up the formula for the lift, we see that there's gonna be, if everything else remains a constant, and of course in case of some flaps the surface area is going to also increase, but we're not going to go in that in detail. Even if we just presume that the lift coefficient is going to increase, we can see that the lift is also going to increase, and this increase in the lift, this delta lift, is going to be proportionate to the increase in the lift coefficient, so the delta CL. But we can also see that, if you remember, the induced drag coefficient as a formula was the lift coefficient squared over with pi times the aspect ratio, right? We could also have the Oswald factor in the formula, but for simplification we're not going to do that. We can see that the denominator of the function is a constant, we could say that. And however, the lift coefficient, as we saw right here, for a given angle of attack is going to increase, and since it has the square root of the lift coefficient, the induced drag coefficient is also going to increase. So therefore, this is why we have the increase in the drag as along with the increase of the lift when you deploy the flaps, right? Because this is the induced drag which increases with the increase of the lift, right? Because induced drag comes with the generation of lift. Okay, so we can see that there's two effects, mainly speaking. So we have the increase of lift when we deploy the flaps, and we also have the increase of the drag. Okay, so interestingly, if flap deflection is increased, one of the effects is that your lift is going to increase. Okay, so what does that mean for the takeoff run? If we go back and examine, generally speaking, the takeoff run itself, we can definitely see that the higher the lift force on this drawing, the higher the lift force, basically the higher the weight minus the lift, so therefore the reaction force is going to be reduced, and I'm going to reach my true airspeed, which is required for me to lift off basically at an earlier speed. So therefore, altogether, because in the formula for lift, we have, which for the case of the liftoff is going to be equal to the weight, and it's going to be liftoff, or lift coefficient times the density over 2 times the true airspeed squared times the surface area, right? So if I can increase the lift coefficient, that means for the same amount of weight which I need to lift off, it means that this VLOF is going to decrease. And if I have to accelerate with the same amount of acceleration to basically a lower speed, that means that the distance which is required, or the takeoff run which is required to reach this liftoff speed, is going to be lower. So therefore, my takeoff run is going to be decreased, interestingly. So this is the effect of the extra lift. We could also see that the weight minus the lift is going to reduce, so therefore the friction forces are going to be reduced. And we had the, actually you can write up like the acceleration in the x-axis was the thrust minus the sum of the drag, so the aerodynamic drag, minus the sum of the friction forces over with the mass of the aircraft. So this component would actually decrease, which would increase a little bit the acceleration. So from the lift side, the takeoff run is reduced, which has a positive effect for us. Okay, but the drag is also increased, right? So let's examine what kind of an effect does that have on us, right? So we had this drawing up here when the aircraft is accelerating on the runway, and this drag is increased. What does that mean for us? Well, not so much good, if you can already imagine it. So we can also write again the acceleration in the longitudinal axis. So we have the aerodynamic drag minus the sum of the friction forces over with the mass. Okay, so what happens if you increase the aerodynamic drag? The excess thrust altogether is going to be reduced, right? Because the thrust is basically in both cases unaffected by the effect of the flap. So in this case, the aerodynamic drag is going to be increased, so therefore the excess thrust is going to be decreased, so the acceleration is going to be reduced. So if we don't look at the lift's effect in this case, only the drag's effect, you can see that the takeoff run, which is required, is going to increase and is a negative effect. Okay, so we can see that it's pretty controversial right here because the increasing of the flap or the usage of flap is increasing the lift. It's increasing the lift, which has altogether a good effect for me because it would reduce the takeoff run, but it also increases the drag, which is going to have a negative effect for me, right? So how do I balance these two? How is it possible to balance these two effects? What is the sum of their effects? And this is what we're interested in. Like, what is the sum of these two contradicting effects? Okay, to examine that, first let's look. I'm sure you've already talked about this in Principles of Flight, but let's just draw it up for a second. Let's plot the increment of the lift coefficient and the increment of the drag coefficient in function of the flap deflection angle. Okay, so if you have the lift coefficient increment, what we usually see is a diagram like this. Is that initially there is a large increase which tends to get flatter towards the end of the diagram, right? And when you look at the drag coefficient increment, what you see initially is that at lower flap deflections is going to be flatter, and then it starts increasing as you increase the flap settings, and at some point it's becoming equal. And so this would be your drag coefficient increment. Okay. So what we can see is that for lower flap settings, or smaller flap deflection, we're gonna get a higher lift coefficient increment up here with only a small penalty for the drag coefficient, right? So usually the area which is useful to us is between the two curves. So between the lift coefficient and the drag coefficient, right? So this area right here is the area which is, so to speak, useful for us. This is the increment in the difference between the lift and the drag, right? Because there's no point in further increasing the flaps, because then you would get, more that drag than you would get lift, and there's no point in that, right? So for smaller flap deflections, we're getting a relatively large increment or increase in the lift coefficient and a relatively small drag penalty. Okay, so what happens when we further increase it and look at the higher flap deflection angles? So higher flap deflection. What we see is that after a while around here, the extra lift coefficient which you can get out of the wing is not so great for a unit increment in the flap increase as compared to, for example, initially, right? So let's say right here, or even more visibly even before that. So at this area, if you look at it, is the same unit distance, this one, the same unit distance, and your increase in flap or lift coefficient is this much, and your increase in the drag coefficient is only this much, whereas at this point the increase in the lift coefficient is this little, and the increase in the drag coefficient is this much, right? So what we see at larger flap deflections is that altogether at this point, at this regime, you're starting to generate more and more drag coefficient and less lift coefficient with the addition of 1 unit of flap deflection. So generally speaking, for takeoff, what do we want? For takeoff, we want to generate a lot more lift coefficient, so we want a lot of this good effect and a lot of this good effect and little of the negative effect. So it's pretty visible that we're going to be using this side, the initial side of the regime, right? So this one is for takeoff. As for the lower flap deflections, we're going to be using the smaller flap deflections. And for the landing, as you have talked about in Principles of Flight, you're going to want to create the largest lift coefficient as you possibly can, because you want to reduce your touchdown speed as much as possible, even with a high penalty of drag. Therefore, for the landing, you're going to be using this regime right here, right? So the larger flap deflection. This is what you're going to be using for landing. About the landing, we'll talk much later. But basically what you can see is that for the takeoff, we're going to be using the smaller flap deflections. So this we discussed, but let's see exactly how this whole thing sort of affects the takeoff run and the takeoff distance. So exactly how much flaps are we using? Because this is an interesting question. Okay. So let's draw like a side view profile of a runway. So here's your runway right there. Zoom onto it nicely. Okay, so here's your runway. Okay, so we have, let's say, an initial aircraft which is taking off from the brake release point, and this, let's say, this orange line is the zero flap deflection. So you have a given amount of takeoff run. Now let's make it a little bit longer. So you have a given amount of takeoff run. This one is a takeoff run, and with the zero flap deflection, and this is your airborne section, and this is your screen height. Okay, so this is your airborne section. What happens if I add a little bit of flaps? Let's say 5 degrees. Okay, brake release point is going to be the same. So since we're at this region still of this curve, we got to say that the lift coefficient is going to increase by a larger amount, and the drag coefficient is going to increase by only a small amount. So therefore your takeoff run is going to altogether be decreased, because we get more of this good or positive effect rather than this negative. So we get more of the positive, so therefore the aircraft is going to have a reduced takeoff run. And so just to make sure that this one is clear, this is not takeoff distance, this is takeoff run. So this is the takeoff distance. Okay, takeoff distance. Okay, and the pink one is going to be for the 5 degree flap deflection. We'll have to establish right here that basically any flap setting is always going to reduce the climb capability. We're going to go into this later, but if you just remember real quickly, the sign of the gamma, so during the climb, the sign of the gamma was the excess thrust, so basically thrust minus the drag over with the weight. Okay, so what happens when you increase the flap deflection? Drag increases, thrust is unaffected, so altogether the thrust minus drag is going to decrease, so therefore, and of course the mass is unaffected, so therefore your flap deflection angle is going to reduce. Like anytime you use a flap deflection, let's just sort of go into a bit of detail here. So let's say here you have the ground, here you have don't know, like an obstacle of some sort, and your flight path angle. Right, so you remember that the flight path angle, or sorry, the flight path is the path along which the center of gravity of the aircraft travels along, and the gamma, let's say this is the clean configuration, so delta flaps is 0. So delta flaps is 0, and so flight path is again the path along which the center of gravity of the aircraft travels along, and the flight path angle is the angle between the flight path and the local horizontal. And so anytime you have other than 0 degree flaps angle, this angle is going to be reduced. So anytime it's not 0, so it's 5 degrees, 10 degrees, and of course based on the magnitude this is going to be reduced. So if you have I don't know, let's say 5 degrees of flaps, so this is your flight path with delta flaps 5 degrees. Let's say you have another one for 10 degrees, and your flight path for delta flap 10 degrees is going to be reduced, right? So your angle is going to be even shallower. And just one quick correction here, this one is not delta, this is gamma right here, and this is with flap deflection of 10 degrees or 15, yeah, 15 degrees. Right, so the more you increase the flap setting, the more the drag is going to increase, and the more the flight path angle is going to decrease. This is the altogether effect. So in this whole gameplay, the takeoff run is going to be decreased because initially, because of this effect, right? So the balance between the two effects, but the airborne section is always going to increase. So if you have here this given amount of distance, this right here, you would have to add a little bit, and this is the amount which I basically gonna transfer right here, right? Because the airborne section is going to be increased with this amount, let's say. And right here, I reach the screen height. And right here, I reach the screen height. And this is the initial effect. So the final effect is that my takeoff run right here is going to be reduced compared to the initial one with the clean configuration. The airborne section is increased, however, still the takeoff distance is going to be decreased still. Okay, so let's look at even further increasing the flap setting. So if I increase the flap setting even further, my takeoff run, so because I'm still at the lower regime right here, this is gonna mean that my positive effect with regards to the takeoff run is still gonna be outweigh the negative. But of course, at this section, when you go to higher sections, this is going to be the case less and less, right? Because the penalty for the drag coefficient is going to be higher and higher with every single addition of flap increment. So therefore, my takeoff distance is going to be reduced, less amount than the previous one. So this is going to be less, but still decreased. So this would be the delta flap 15 degrees. And of course, this was the previous airborne section, so this one. If I increase it just a little bit, like so, this is what I would have to add right here, right? Because the airborne section, because of this effect would still be increased, but altogether, as you can see, here's my screen height right here. And I connect the liftoff with the screen height, and what I can see is that my takeoff run is reduced. My takeoff run is reduced, and the airborne section is increased, however, still because of the positive effect of the takeoff run, my takeoff distance is still reduced. Okay, so here's when it gets interesting. We can consider a scenario, let's say flaps 20. All begin from the brake release point, and we can say that altogether it can happen that the takeoff run is still a bit shorter at this point. However, the airborne section is going to be increased further. So we're comparing with the with this one. Basically, the green one is going to be our previous airborne section. So we add a little bit to it. So this amount, just a little bit, and then I know it's getting a bit chaotic, but we just add that right here below. And what I wanted to show you, just a detour a little bit, is that we saw an increase, or sorry, a decrease in the takeoff run, but the increment is getting smaller and smaller and smaller. So initially we gained this much of takeoff distance or takeoff run reduction, and after that we only got this much. So the effect on the takeoff distance is smaller and smaller, and this is when it becomes interesting, is that we can have a point where the takeoff run is still reduced, but from here there's the screen height, the takeoff distance altogether is larger than in the previous case, and after a while it's going to happen that the takeoff run can actually be, you know, larger as well. But even if it's smaller, it does no longer compensate for the increased airborne section, and the takeoff distance altogether is going to be increased. And so you can see that in this case we're going to have like an optimum flap setting, or a flap setting where the takeoff distance is highest, right? So we started increasing the flap setting up to a point where we reach the maximum takeoff distance, and from this, if we increase it further, the flap setting is going to reduce the takeoff distance, right? So it's very interesting. If we wanted to plot that, and this is the one which you will actually find in the PathPilot book, if you want to plot the takeoff distance in function of the flap setting, what you will get is a curve which looks the following way, is that it's going to start to, just one correction, so just to make it clear, this one is a takeoff distance. So altogether, takeoff distance has some amount, is reaching a given value, and if you increase the flap deflection, is going to start to decrease, right? But the rate of decrease is getting shallower and shallower because of this effect, right? So initially you're getting a large decrease by a given increment of flap, and after that a smaller decrease, right? And it's going to reach a point, it's going to reach a flap deflection when takeoff distance, sorry, here another correction, so this is takeoff distance min, right? So this is takeoff distance minimum, so the smallest amount of takeoff distance. So where the takeoff distance is going to reach a minimum, and after that is going to start to increase again. And this is your function for the takeoff distance. Okay, so just as a representative value in the PathPilot book, you have some basically example flap deflection values. So in the book it's 5 degrees, it begins at 5 degrees, You have 15 degrees when it's reaching its optimum value, the takeoff distance, the minimum value, and it ends around 25 degrees. So this one is just an example, and it is representative of no aircraft, right? So these values are going to be different for every single aircraft, but just to have some sort of consistency, these are the numbers that we're gonna sort of go with. Okay, but I just wanted to highlight it out. But what's important here is that the takeoff distance curve, if you wanted to plot it in the function of the flap deflection angle, would look like this diagram right here. Okay, so the next main area that we need to discuss is with regards of the takeoff and the flap settings is the mass limitations. The reason why we have mass limitations is that, if you remember, on our last classroom session we talked about the effect of mass on the takeoff, right? So what we said, if you increase the mass, your takeoff run and your takeoff distance is going to be increased, right? So we saw that it had a negative effect on us, so the mass has a negative effect. However, since this is a commercial flying, we also said that you want to increase the mass as much as possible, right? So you want to increase the mass because it's going to have within like two things. One is the amount of fuel you're taking and basically the useful load that you can take with you. So this one would include any passengers, their baggage, luggage, any cargo that you would be taking. So of course the passengers along with their baggage and the cargo and everything, is getting paid for. And of course you want to take fuel because you want to get to your destination, you want to have your alternates. But one other example is that the more fuel you can take with you, the more range you're going to have. About this we're going to talk later. But just to get the initial idea, the more range that you can have, the more distant and sometimes maybe more exotic places you can go to. For example, from Budapest you can go to Iceland, and from Budapest you can also go to Dubai with Wizz Air. And these are fairly exotic destinations. And so you can sell these tickets, of course, more expensively. And this is also another way for commercial companies to generate revenue, right? To offer more exciting further destinations, right? So for that, you also need to carry more fuel. So therefore, from commercial perspective, having more mass is beneficiary because that's what's generating revenue. Right? That's what's revenue generating. But from performance point of view, having more mass is bad, right? Because it's going to increase the takeoff run and the takeoff distance. So what we're going to have is basically limitations from multiple sides. So the first limitation, which you have already might have heard of, so for the takeoff, so this one is for the takeoff, is the so-called, so the first one is the structural limitation, and is the so-called maximum takeoff mass, or sometimes referred to as a maximum takeoff weight. So MTOM is the maximum structural, it's not always referred to that, so maximum structural mass, maximum structural take off mass of the aircraft, right? This is a structural limitation, and it's basically is a constant. It's given, based on structural calculations. This is the amount of mass that the aircraft can still take off with, so this is a basically constant limitation. Okay, however, we're not just going to have structural limitations, we're also going to have performance limitations. And this is where it's going to become interesting. So we're going to have performance limitations. And from performance part, we're going to have the performance limited takeoff mass. So performance limited takeoff mass is going to be a performance limitation. Take off mass. And this is going to have two sides to the story. One is going to be, the first one is the runway limited takeoff mass. So the runway limited takeoff mass, takeoff mass, and the second part is going to be the climb limited takeoff mass, CL2. So climb limited takeoff mass. Okay, so I think the structural limitation is fairly understandable. I won't elaborate on that, but the performance limitations, let's talk about that just a little bit. So the first one, runway limited takeoff mass. What is the correlation of mass and of the takeoff mass with, for example, the takeoff distance, takeoff run? Because essentially these two are what are going to give us the runway limited takeoff mass. Let's imagine that we have a nice runway. We have the runway right here, denoted in the usual way. We have our little airplane, and right here is a nice pink airplane in the brake release point. And let's say that this is the takeoff distance available. So let's not take any clear way, stop way into consideration, but let's just do one. Let's say that at a given mass, you have the takeoff run, the airborne section, you reach the screen height, and this is your takeoff distance, with this amount of mass, with a given amount of mass. Okay. So what you can see, or what we have already talked about, is that if you increase the mass, your takeoff distance is going to be increased. So therefore, from this point, if I went and increased the mass of the aircraft, from the same brake release point, it would increase the takeoff run, but also the takeoff distance, right? Like this. So your takeoff distance from this point would be increased. So the takeoff distance m plus. Okay, so we can still see that there's some like space right here. So if I further increased my takeoff mass from the brake release point, my takeoff run would increase and my takeoff distance would increase. And let's say that they're just exactly equal to each other. We're not going to talk about safety factor for now. We just want to get the roughly speaking the point. Okay, so in this case, in this green case, my takeoff distance with the basically, let's say 3 pluses, because I have both of these additions, is just equal to the takeoff distance which is available. Like, can I further increase the mass of the aircraft? Well, can I? In that case, yet again, if you increase the mass, your takeoff run is going to increase and your takeoff distance is going to increase, right? So let's try that. You know, if we added the extra mass, your takeoff run would increase, and you know, your flight path angle is becoming shallower, so your airborne section is also larger. So you reach the screen height outside of the takeoff distance available. So I started here from the brake release point, and therefore your takeoff distance at the M, I don't know, plus, actually I like 5 pluses, is going to be larger than the takeoff distance which is available. So that is not good. So what we can see is that I'm going to have a mass limitation with which I can just barely make the takeoff distance with any required safety factor, because in reality we're not going to have, you know, we're not going to go right on the edge. We're not going to be allowed to go right on the edge, but in reality we might have some, or you know, some other safety factor right here, right? It's a safety factor. And basically this amount of mass which you're allowed to take with you in such a way that you can reach your screen height within the takeoff distance available with any required safety factor is called the runway limited takeoff mass, right? Because it's a takeoff mass limitation imposed to us by the runway. And this is going to be a function of basically the runway limited takeoff mass of density is going to be affected by runway surface, is going to be affected it's going to be affected by the wind, very important, by the wind. So it's going to be affected by quite a few factors, and so these things can change from day to day, within a day, of course, you know, from minute to minute basically. So this runway limited takeoff mass we always need to calculate basically, right? We always need to calculate this because it's going to be dynamically changing, because it's dependent on the performance of the aircraft. So this one is a constant and this one is dynamic basically. It's a function of a whole you know, different other functions, right? So this is dynamically changing, both the runway limited takeoff mass, and we'll see the climb limited takeoff mass as well, right? So this is for the runway limited takeoff mass. Let's look at the climb limited takeoff mass. Okay, so let's talk about the climb limited takeoff mass. So to talk about the climb limited takeoff mass, let's imagine a nice big plane, and somewhere right here we have the runway. So the aircraft has taken off, reached the screen height right here. So we've taken off, we reached the screen height, and this is where we'll draw up the flight path angle from, or the flight path of the aircraft. So let's say that from here we're gonna have, let's draw a steeper one, a flight path, not even steeper one. So here we have a flight path, let's say with a lower mass, so low mass. Okay, so flight path is yet again the path along which the center of gravity of the aircraft travels along. Okay, so what happens when I increase the mass of the aircraft is that I'm gonna get a flight path which is essentially lower, right? Because just remember sine of gamma, so the flight path angle is going to be the thrust minus the drag over with the weight. So from one side the mass, so weight is of course mass times gravitational acceleration, which is a constant. So if I increase the mass, that's going to increase the weight, which is going to decrease the flight path angle. But also when the mass is increased, the drag is also increased, so therefore the the excess thrust, this part, is decreased, which further decreases the flight path angle. So we can definitely see that if I add mass to the aircraft, the flight path is going to be shallower, right? And the flight path angle is going to be reduced, because this was the initial one. This was the initial flight path angle, and the flight path angle with the higher mass is going to be reduced. And the reason why we have to have a limitation to this is if I have an obstacle along my takeoff flight path. So this is an obstacle, and we said that we have something called obstacle clearance, and the obstacle clearance is basically the vertical distance between the highest point of the obstacle and the flight path, right? And this is the initial one, the obstacle with the lower mass. And so what happens if you have an increase in the mass is that this obstacle clearance is going to be reduced. And every time you add mass to the aircraft, let's say that this is an even higher mass, the flight path angle is going to be further reduced, the flight path is going to be further reduced, and the obstacle clearance is going to be even further reduced. And it's very visible that this is not going to be very beneficial for us, especially when the pilot doesn't see the obstacles ahead of him or her, when you're flying in, for example, cloud or fog or any kind of weather phenomena which would reduce your visibility. What it does is that by regulation for commercial air transport for Class A and for multi-engine piston Class B aircraft, we're going to have what is known as a minimum obstacle clearance requirement, right? And so therefore this is going to give us a mass which is just going to meet the minimum obstacle clearance requirement on the limitation mass, right? So at this mass, the flight path just exactly meets the minimum obstacle clearance. So your obstacle clearance with this mass is exactly your minimum obstacle clearance, and it occurs at the so-called climb limited takeoff mass, right? It's very interesting. Okay, so from the first portion, from this runway limited takeoff mass, we have already seen that the takeoff distance, how does it change with the increment of flaps? And this is what we're going to talk about, is because flap is going to affect both the runway limited and both the climb limited takeoff mass. Okay, so just to draw it again, here we had the initial diagram, the takeoff distance in function of the flap deflection, which looked like this. So we had initial takeoff distance value, it decreased until a point where it started increasing again, and the values were basically 5 degrees of flaps, 15 degrees of flaps for the lowest, so the takeoff distance min, and this was 25 degrees of flap setting, right? So what we said initially, so here what we're gonna have is the runway limited takeoff mass, is that if the takeoff distance which is required from the airplane side is lower, I can basically take more mass with me. And if the takeoff distance which is required is larger, the mass that I'm allowed or required to take with me is gonna be less, right? So therefore there's an inverse relationship between the two, and that's exactly how you will find it in the Pad Pilot book, or basically any other ATPL book as well. is that, so let's use the same example values as you will see in the Path Pilot book, so 5 degrees, 15 degrees, and 25 degrees. So there's an inverse relationship between the two. So the runway limited takeoff mass has a given value, and it starts going to increase. So this one is a limitation of how much you can basically take with you, how much mass you can take with you. And it's going to decrease after this 15 degrees of flap setting. And what you can see is that from the runway side, this 15 degrees of flaps would be the most beneficiary because the more mass you can take with you, as we have initially said up here, is going to be the better because the more revenue you're gonna generate, right? So from the runway limitation side, this flap setting, this 15 degrees of flap setting would be the most optimum, basically. But we don't only have the runway limited takeoff mass, we also have the climb limited takeoff mass as well. And so the climb limited takeoff mass is going to be, let's just draw it right next to it. This one going to be a smaller one. So the climb limited takeoff mass. We said in this case that anytime that you add flaps, or anytime if you add mass, so the flaps case we had up here. So anytime you add flaps, your flight path is getting shallower. And any addition of mass is basically also going to shallow out your flight path. So the biggest amount for any given mass, so if the mass is fixed, if the value of the mass is fixed, what that's going to mean is that the limited takeoff mass is going to be largest when the flap deflection is basically 0. And anytime you start adding flaps, as we saw before, it's going to reduce your flight path angle and reduce your obstacle clearance. So therefore your climb limited takeoff mass is going to reduce in a monotone manner, so it's a continuous reduction in the climb limited takeoff mass. Right. So one thing I still want to mention is that we said that this performance limited takeoff mass is made up of this runway limited takeoff mass and the climb limited takeoff mass. And the way it is made up of these two sort of values is that we're going to say that the performance limited takeoff mass is the lower of the climb limited takeoff mass and the runway limited takeoff mass. And I think it makes sense if you think about it from a practical point of view, right? If you have like enough mass to take off from the runway within the takeoff distance available, but you basically cannot maintain the obstacle clearance from an obstacle or from terrain, so you basically crash onto the mountain later, that's not really good. So that would be the case that you meet the runway limited takeoff mass, but you do not meet the climb limited takeoff mass. In that case, you know, you're gonna crash basically, right? So this is not an option. It's not an option. So what happens in the other case when your climb limited takeoff mass is met? So you can maintain the minimum obstacle clearance from the obstacle, but you cannot take off within the takeoff distance which is available. So basically, you don't meet the runway limited takeoff mass criteria. You're going to basically overrun and cause a runway incursion. In a better case, in a worst case, that could lead to a very bad accident, maybe explosion of the fuel, or something horrible. So this is not an option either, right? So what has to happen is that you're going to have to satisfy both these requirements, even if it means that there's going to be, like, you could carry more mass, let's say from the runway limited takeoff mass point of view. So you could still increase your mass because you would have, you would satisfy the takeoff distance criteria, but if you would do that, you would further decrease your flight path angle and you wouldn't meet your obstacle clearance criteria. So there's an extra buffer basically only from one side of the limitations, and you're just barely meeting the other one. But you have to meet both requirements, and this is going to mean that your final performance limited takeoff mass is going to be the lower of these two values, right? And this is what's interesting here, right? Because you have to meet both sides. So it's already pretty much visible where we're going with this, is that we're going to plot both of these two diagrams basically in the same coordinate system. So we have the flap deflection, and we have, I'm going to use the same colors as it's in the Path Pilot book. So we're going to have the climb limited takeoff mass with the blue and the runway limited takeoff mass with the red color. Okay. So the runway limited takeoff mass looks the way it does. It looks like this. So it's an initially like increasing value up to a point, after which it's going to start to decrease basically. So this is your runway limited takeoff mass. And your climb limited takeoff mass is going to be a monotonously decreasing value with the increase of the flap setting. Okay, so let's look at different basically flap settings to examine what is going to be our performance limited takeoff mass. Okay, so let's say that we're going to be using this delta flap, X maybe. Okay, so along this line, we're going to have two limitations. So the first limitation is imposed to us by the climb limited takeoff mass, and the other one is imposed to us by the runway limited takeoff mass. So which one is going to be the final limitation? We said that by definition the performance limited takeoff mass is going to be the lower of the climb limited takeoff mass and of the runway limited takeoff mass. So at this point, your performance limited takeoff mass is going to be the lower, so therefore the runway limited takeoff mass at this point. So let's go on a bit further. So let's examine this flap setting. Let's say delta fx plus 1. So in this case, we're going to be limited from above by the climb limited takeoff mass, and we're going to have a lower limitation, the runway limited takeoff mass, and so therefore the performance limited takeoff mass is going to be the lower of the two, so the runway limited takeoff mass. Okay, let's examine what happens right here at this point. So delta fy, let's say. I have two limitations yet again, the runway limited takeoff mass and the climb limited takeoff mass, and by definition the performance limited takeoff mass is going to be the lower of the runway limited takeoff mass and the climb limited takeoff mass, so it's going to be at this point right here, so the climb limited takeoff mass. Okay, what happens if I go a few steps further to delta fy plus 1? I have the runway limited takeoff mass and let's use this color instead. So from above I have the runway limited takeoff mass, the climb limited takeoff mass, and of course the lower one is going to be my limitation. And what's going to happen at this point, and I'm not going to give it a name for the flap setting just yet, is that we're going to have the runway limited takeoff mass exactly equal the climb limited takeoff mass, and this is going to be our performance limited takeoff mass. So what we can see is that we have a lower flap setting than this one, in that case, the runway limited takeoff mass is going to be the more limiting. So therefore, if I connect the points, basically this is the curve that I get. And if I use higher flap settings than this current one, the climb limited takeoff mass is going to be the more limiting one. So therefore, it's going to look like this. So what I can see that altogether the useful area for me is from where I can choose takeoff masses, final actual takeoff masses, is below this area, right? Is below this area, below the performance limited takeoff mass. Because what happens if I'm at the delta F flaps X setting, so this one, and I choose a takeoff mass which is right here. Okay, so my takeoff mass in this case would be below the climb limited takeoff mass, which means that basically I can achieve the minimum obstacle clearance during climb, right? So it's what it means. However, I'm going to be above my runway limited takeoff mass. So what that means is that during my takeoff, I'm going to overrun the runway, right? So this is not a good value. What I can choose maximum is the runway, is the performance limited takeoff mass. So the green line basically is the performance limited takeoff mass. Okay, so what happens if I choose a mass over here, right? So if I choose a mass over here, I'm going to be below the runway limited takeoff mass, which means that I will be able to achieve my screen height before the takeoff distance available, and plus, you know, the safety factor if there is any. However, I will be above my my climb limited takeoff mass, which means that I'm not going to be able to clear any obstacles in the takeoff flight path. So either my minimum obstacle clearance is going to be impaired, or actually I go on and straight have contact with any obstacle or terrain in the takeoff flight path. So meaning I would have a crash, right? Not so good. And what happens if I choose, you know, at this delta Fy flap setting, a mass corresponding to this one? I can do that, right? Because it's going to be below both my climb limited takeoff mass, below both the blue one and both the red one, the runway limited takeoff mass. So I can go ahead and actually choose this mass if I want to, right? But there's going to be an increment in mass between the performance limited takeoff mass and my actual mass, where if I wanted to, I could add more mass so that I can generate more revenue, right? So this is not an efficient mass for these kind of conditions that I have. So therefore, it's always useful for me to basically take the most mass as possible. So at the different flap settings, we can look at the different mass limitations, the maximum amount of mass, and I want to optimize, I want to find the flap setting where my performance limited takeoff mass would reach its maximum, right? So this is what I'm looking for, and it's very easy to basically find it on this drawing, because where I reach the most amount of performance limited takeoff mass, or my performance limited takeoff mass is maximum, is where the runway limited takeoff mass is equal to the climb limited takeoff mass in this drawing, and where I reach the highest performance limited takeoff mass is maximum. Because if I were to choose, and this is why I didn't give it a name officially, or not officially in the beginning, is because we're going to call this the optimum flap deflection angle, this one, for the takeoff. And the reason it's an optimum is because it's an optimum between the runway limited takeoff mass and the climb limited takeoff mass. Because if I choose a lower flap deflection, my basically performance limited takeoff mass is going to be less at any given point at a lower flap deflection. And if I use a larger flap deflection, my performance limited takeoff masses are going to be below it, right? So what it means is that at this optimum flap setting, I achieve the highest performance limited takeoff mass. Okay. What's also interesting to note is that below the optimum flap setting, the climb is going to be more limiting, quite the contrary. So below the optimum flap setting, the runway is going to be more limiting, right? Because at lower flap settings, my takeoff run and my takeoff distance is going to be larger, but because I have low flap setting, my climb is going to be more steeper, but my takeoff distance is going to be initially larger, right? But after above the optimum flap setting, we can see that actually it's the climb which is more limiting, which makes sense because the further you're increasing your flap setting, the shallower your flight path is going to become, and the more reduced your obstacle clearance is going to be, right? So I think this makes sense. Okay, so usually you can get questions which require you to find the optimum flap angle, and basically these questions come in a table format, for which we will see an example right now. So you can find this example in the PathPilot book, and with the help of editing, I'll just magically put this table right here in a second. Okay, so poof, there you have it. You can find the same exact table in the PathPilot book. So you can see that we have three main sources of information. So the one thing is the first column, you have the different flap settings. So every single column basically belongs to a given flap setting. So this column right here belongs to the flap setting of 5 degrees. So you have, for the 5-degree flap setting, the given runway limited takeoff mass. So this is the second information, and also you can see the climb limited takeoff mass in the third row, basically. And you have the same type of information for flaps 10, flaps 15, and flaps 30 degrees. Okay, so what we're trying to find is the usually how the question is made is that you need to find the maximum performance limited takeoff mass, and you need to also find the optimum flap setting. So these two are the question. Okay, so how we solve this problem is first finding the performance limited takeoff mass for every single flap setting. So it's a very similar solution to this graphical one like we saw before. So we go through each and every flap setting and we'll just find the performance limited takeoff mass. Okay, so for the first one, 5 degrees, and we have runway limited takeoff mass 55 tons, and we have a climb limited takeoff mass of 60 tons. Okay, so what was the definition of performance limited takeoff mass? Let's take a look at it again. So performance limited takeoff mass right here is the lower of the climb limited takeoff mass and the runway limited takeoff mass. Okay, so the runway limited takeoff mass is 55 tons and the climb limited takeoff mass is 60 tons. So which one is going to be your performance limited takeoff mass? The lower of the two, so of course the runway limited takeoff mass with 55 tons. Okay, so let's move on to the 10-degree flap setting. So you have runway limited takeoff mass of 56 tons and the climb limited takeoff mass of 57.5 tons. So which one is going to be the lower one? of course, the lower one is the runway limited takeoff mass with 56 tons. So if you look at the next, in the 15-degree flap setting, you have the runway limited takeoff mass with 56.6 tons and the climb limited takeoff mass with 55 tons. Of course, the lower one is the climb limited takeoff mass is the 55 tons, and we're going to do the same thing for the 30 degrees of flap deflection. The lower one is the climb limited takeoff mass with 52.7 tons. Okay, so what we were looking for, what we said by definition, the optimum flap setting, delta flap optimum, what it gives us right here, if you remember, is the maximum for the performance limited takeoff mass. So we need to find the maximum value that this performance limited takeoff mass reaches. So we have the 4 values for each flap setting. So 5 degrees for 55 tons, 10 degrees for 56 tons, 15 degrees for 55, and 30 degrees for 52.7. And it's very convenient to see that the winner is the 56 tons, is the highest from these performance limited takeoff masses, and it occurs at 10 degrees of flaps. So therefore, this 56 tons is going to be your maximum performance limited takeoff mass, and this is the final one actually. It's 56,000 kilograms, and the flap setting is going to be the optimum one, is because this is where the largest performance limited takeoff mass occurs. And you can remember it simply speaking that the performance limited takeoff mass maximum is going to be the highest of the lowest values. Sorry. Is the highest of the lowest values, right? Because you go through each flap setting, and in each flap setting you choose the lower values, and from the lower values you choose the highest value, right? So it's going to be the highest value of the lowest values. Okay, I hope it makes sense. If you look at it, we did the exact same kind of optimization as we did up here graphically. We went through each of the flap settings. We looked at the lower of the climb limited and the performance limited takeoff mass, and we made the performance limited takeoff mass equal to the lower of the two, and that became our sort of performance limited takeoff mass. And then we were looking for the optimum flap angle, where this performance limited takeoff mass were the highest. And this is what we did, but just in a table format, and this is sort of the format which you can expect to get during aviation exam and CAA questions. Okay, so just to recap what we have talked about in this video. So roughly speaking, we talked about the effect of flaps on the takeoff distance and the takeoff run. So we saw that it's going to essentially increase both the lift and the drag. So on the takeoff run is going to have like two effects. So the increase of the lift is going to decrease the takeoff run, which is a positive effect, and the drag is going to increase the takeoff run required. So generally speaking, in any type of airplane, we're going to use the lower flap settings for takeoff and the higher flap settings for landing. And on the airborne section of the takeoff or the climb, basically the effect of takeoff or the effect of flaps is always going to be negative. So we looked at different cases, and we concluded that the takeoff distance is going to be decreasing until some amount of flaps, and after this amount of flaps the takeoff distance is going to increase, because the decrease in the takeoff run is no longer able to basically counteract the increase in the airborne section because of the degraded climb caused by the flaps. And so this was the initial part, and we also spoke a little bit about mass limitation. So we had the structural limitation, the maximum takeoff mass, and more importantly, the performance limitations, which were made of by the performance limited takeoff mass, which is the lower of the runway limited takeoff mass and the climb limited takeoff mass. And we saw that both of the climb limited takeoff mass and the runway limited takeoff mass are going to be a function basically of the density of the wind. Of course, by the runway surface, it's only the climb limited takeoff, or sorry, the runway limited takeoff mass, which is going to be affected. And so we have to calculate both this runway limited and the climb limited takeoff mass for every single scenario, for every single takeoff. And we also saw that the runway limited takeoff mass was an inverse, basically, of the takeoff distance and its effect by the flaps. So we saw that the runway limited takeoff mass was maximum, where the takeoff distance was minimum. And we also saw that the climb limited takeoff mass was just continuously decreasing as you were adding flaps. We put these two in the same diagram, and we concluded that at the lower flap deflections is going to be the runway limited takeoff mass, so the effect of the runway, which is more limiting for the takeoff, and at higher flap settings is going to be the climb, which is going to be more limiting. And between the two, we're going to have an optimum flap setting where our performance limited takeoff mass is going to be the highest. So therefore, that's going to be our most efficient takeoff mass and the most efficient flap setting. And we also looked at how to optimize this in case of a table format exercise. So generally speaking, flaps, some amount, lower amount is good for us because it's reducing the takeoff run, but higher amounts are usually bad for us because after a while it's also gonna reduce the takeoff, or sorry, increase the takeoff distance and degrade the takeoff climb. And what is very important to remember is that the airborne section of the takeoff and the climb is always going to be affected by the flaps. So if you have flaps any other configuration than clean, you're going to reduce your climb capabilities. And this is what is very important. But you can reduce your takeoff run, reduce the time you spend on the ground. Okay. And that was it for this video. I'd like to thank you for your attention, and that's it.